My name is Oleg Šelajev, and a big welcome from me here. We're going to talk about cloud-native Java microservices with GraalVM, which is a topic very close to my heart. I like it very, very much. And yeah, I hope it will be interesting for you. We will have 50 minutes for the session. I assume there will be some questions. Usually talks about GraalVM produce quite a bit of questions. So don't be shy, ask them immediately in the chat. I will try to monitor it. I will keep like half an eye looking at the chat. But if anything else fails, we're gonna address them at the end of the session and we will still be in time. So without further ado, let me start. So let's talk about cloud native Java microservices with GraalVM and at JCon. If you have any questions that you want to ask later, you can find me on the internet. I go by @Šelajev, and yeah, we're gonna have a chat. So just recently, literally 3 days ago, or actually 6 if you count the wall clock, I changed jobs and I was on the GraalVM team for quite a bit. And then I joined the Atomic Jar, which is a startup that works on test containers, and the mission is to make integration tests better, easier, faster, and more popular in the industry. This is really interesting technology. I can show a quick demo of that somewhere later in the session where appropriate, but just know that I'm no longer affiliated with Oracle or GraalVM team directly. However, I stay a big fan of the project, and I would like to see it succeed, and I would like you also know about it more and more. So what is GraalVM? When we talk about GraalVM, we need to understand that this is a collection of technologies. Why they are under the same umbrella of the project? It's because they work together and they were created as the implication of the same technology. So what is GraalVM? GraalVM is a distribution of a runtime. You can use it as your JDK. You can use it to run your Java applications, and it runs with the state-of-the-art just-in-time compiler. So it runs Java Hotspot Virtual Machine as your normal OpenJDK distribution does, but it replaces the top-tier, most optimizing JIT compiler with a custom implementation that is written in Java, that is more modern, maybe more powerful in certain scenarios, gives you performance boost when you run your applications and when the JIT compiler takes the code and optimizes it. So you can get the performance boost out of this way. Also, the same compiler can be used in the ahead of time setting. This is where you analyze your application and you compile it before you actually start running it ahead of time. Why is it in the same GraalVM project? Because it uses the same technology that is developed there. So this is 2 different applications of the same compiler technology. So you can use that, and then the applications compiled this way will have a different performance profile, which means they will be faster to start. They don't depend on the JVM, external JVM to run. They are standalone. They have a flat performance profile. All those characteristics are very, very good for certain deployment scenarios. For example, when you deploy into the cloud. This means that this is what we're going to talk about here on the session, about applying GraalVM to compile your applications ahead of time into the binary, deploying to the cloud, and how to do that, what to know about this, and what are some of the best practices of how to do this. And also the same compiler also powers compilation of all other languages supported on GraalVM. There is a framework for implementing languages called Truffle, and there are a number of languages implemented on top of that: JavaScript, Python, Ruby, R, WebAssembly, even the Java bytecode interpretation and running through Truffle is also available as a project. So there are a number of use cases that the same technology powers. At the heart of the GraalVM project is the compiler, and it powers all 3. We're going to concentrate on ahead of time compilation today. There are a number of things that you can do with GraalVM. We tried quite a bit to educate people and explain what it does. So you can check the medium.com/GraalVM blog. There are a number of materials of how to use things. I hope they're quite useful. We will see. But in a nutshell, how do you use that? You have to download GraalVM. As any other runtime, you need to download it and install it. GraalVM package that you can download comes in 2 different flavors. There is a GraalVM Community Edition, which is the open source distribution made by the GraalVM team. It's available under the open source licenses. There are different components. You can download that. It's available for all major operating systems. And I see Matt is asking there if there is a GraalVM distribution available for Mac on M1 chip in the testing. Currently, there is no specific distribution for M1. However, the normal Intel AMD chip macOS distributions would work on the Mac. This is a Mac. I'm going to show a couple of demos. Hopefully, it will all work. So the versions of Java that is available when you use GraalVM are 8, 11, and 16 currently. 17 was just released like a few weeks ago. The next release of GraalVM is supposed to have the 17's downloads available. You can also access the early access builds, like a sort of a nightly packages if you really want to try and run 17s. But most reasonably used versions of Java are covered, and you can use that. And there is also the GraalVM Enterprise Edition, which is a proprietary product by Oracle, and it differentiates mostly by having a more powerful, more sophisticated compiler, which gives you better performance for other languages, better performance when you build native images, and there are some features related to performance or other enterprise features like sandbox for executing languages that is available in the GraalVM Enterprise Edition. You can use that for free of cost on Oracle Cloud, which is what I will use for my personal reasons when I need to use GraalVM Enterprise somewhere in the cloud environment. Java 17. So the versions of Java that are available are the same: 8, 11, 16, 17. I think it's supposed to be GA in the next release. The next release will be in October. So it usually follows, it's a 3 months based cadence. So there are 4 releases a year, and they're usually 1 month after they coincide with the CPU release for OpenJDK. So in October, like one of the Tuesdays in October, there will be a release and some information. I think 17 is supposed to be GA there, but I'm not sure. There are different components, right, to the GraalVM distribution. So the compiler is probably the simplest because it's the first thing that needs to work to enable all other use cases. Native image is probably the second, because other languages, for example, sometimes need to have the native launchers. And even in the default GraalVM distribution, what they do now, what we as a community do, we take the GraalVM compiler, which is written in Java, we compile it with native image into the shared library, and we load that shared library into the native JVM code. So it doesn't load the compiler as a jar file. It doesn't need to just-in-time compile the compiler. It uses a separate heap for its own data structures and everything. So there is a better separation and a more flat performance profile for that. So hopefully 17 will be GA. Cannot tell you what's exactly like that. How do you get started? Very simple. You download the archive, you unpack it, you put it on the path, and you run it normally. There is a Java launcher in the bin directory of the GraalVM. You just run it normally for your application. It will be configured with the GraalVM compiler automatically. You don't have to do anything. It's a compatible JDK distribution. So the team runs a ton of tests. The team runs a ton of benchmarks. They do run a lot of code, different code. And so your application most probably just works out of the box because it's a compatible JDK. Really, the The difference there is that the just-in-time compiler will kick in and make your application faster eventually, for various definitions of faster. You should explore that. How much faster? On the real-world workloads and benchmarks, we see quite a bit of speed up on certain workloads. One of the benchmark seats that I like to recommend looking at is Renaissance benchmark seat. Why? Because it consists of the benchmarks from different open source projects in the Java ecosystem that are commonly used currently. Right? We would like to concentrate very much on the benchmarks, on the code that you currently run in the applications. And then, so maybe if you're running tight math code, maybe those results are not something that you can extrapolate on your workloads. But then again, you have plenty of other benchmarks that are very much testing that type of code. All the industry-wide accepted da capo, spec benchmarks, everything else, right? So here on the Renaissance, you can see that there are some benchmarks from Akka, there are some benchmarks from Neo4j, there are some reactive extensions benchmarks. So quite a bit of diversity in the workloads that they run. And also those benchmarks were picked in a very interesting fashion. They stress different parts of the JVM. Some of those benchmarks are memory intensive. Some of the benchmarks are like explore task parallelism or data parallelism. Some of them explore multi-threading, and you can see that there are differences in workloads and performance numbers. On average, right? If we take the average temperature at a hospital, which is the number that no one should base their conclusion at, right? So it's not something that makes very much sense. Then GraalVM Community Edition is a little bit faster than OpenJDK with some volatility. So some workloads are considerably faster, some workloads are a little bit lagging, and the GraalVM Enterprise Edition almost universally is faster. So it's yeah, you can safely try GraalVM Enterprise on your workloads and expect performance boost out of that. Of course, this means that the JIT compiler needs to actually do its job, so the workload has to be a little bit longer than a few seconds. You can reasonably simply test the differences because you can install different JVMs, different JDK distributions on your machines or your testing environments, and then just switch and run Java from either one distribution or another. Obviously, as Daniel points out in chat, there is only one current entry in the path that can point to Java, right? Path works on the first comes, first served. So you might want to like check for any confusion there, but it's reasonably easy to change the path or to run the particular like direction manually, right? So if I know where my GraalVM is, I can just full path to Java from there. And then features that make Enterprise Edition faster than the community are mostly there is better inlining. There are optimizations. There are different optimizations, and it's not really easy to like highlight individual ones that kind of benefit all workloads. Because truly, even in this small application, if you compile like a small benchmarks and then you look at the output, which optimizations were applied to that code, there are like more than 100 passes of the transformation of that code that the JIT compiler enables, right? So it's the combination of those that makes it really, really good. But in the Enterprise Edition, there is auto vectorization possibilities, both like SIMT vectorization and both the parallelization of loops. There is better inlining, and there are some others. Like, but in a nutshell, like I have it's a very different talk from what I intended to do here now. How like what makes a compiler so good, right? It's really the combination of new or more advanced sophisticated optimizations. So it is not like there is a key to enable the same code do like work faster or the community edition is crippled. It's just much more work has been put in the Enterprise Edition and there are more optimizations that just do their job better, which is fair enough if you ask me, right? So, but we want to talk here about a different kind of environment. We want to talk about the cloud. In the cloud, normal Java workloads and normal Java performance profiles very often are not what we actually expect and want. Why is that? Because the JIT compiler excels when we want the peak throughput, and the minimal latency for processing our requests. That means that other areas of performance, other areas what we think typically what means your applications to be fast, they are a little bit lagging behind of what could be maybe better suited to some environments. Because JIT needs to be worked at runtime, JIT needs to analyze your code, JIT needs to run together with your application to do its job, right? That takes the resources which very often cannot be found in those cloud deployment environments, right? If we want to package our application and put it in a very tight Docker image or container and give it like very little CPU and a small chunk of memory, there's just not enough resources for the JIT to do its job perfectly, because the application also needs to actually process whatever business logic it needs to process. So the ahead of time compilation resolves that challenge very nicely, right? Because everything is pre-compiled, the startup of our application becomes immediate, literally milliseconds. So you can auto-scale your services on demand. The footprint is much smaller because you don't need to run the infrastructure for the JIT. You can also compile some things more effectively. You don't need to maybe load and hold the metadata about the classes, because AUT compilation in the GraalVM case makes some assumptions about how application was built and is running. So you don't have to keep all that data in memory. You also can package it much nicer in small Docker containers. All those benefits, all those values are really handy in the enterprise edition. In the cloud deployment scenarios. Obviously, the enterprise edition and the community edition can compile your applications into native images. That technology is available in both editions, and it works the same way. Just the compilation is a little bit more sophisticated in the enterprise edition. So the fundamentals, this is a very exciting project. This is what Java ecosystem has jumped on since the very first times we announced a few years ago the native image availability. And there are some differences that you need to know to use this effectively. One of those is that when we run our application on the JVM, normally using Java with the JIT, whether this is the GraalVM with the JIT, or whether this is the any other JDK that you're using, you run your application and there is the runtime phase. During the runtime phase, in the beginning, there on the left, there's the startup where the Java virtual machine starts and it does whatever initialization it needs to do, and then it starts executing your application. That phase could be small, that phase could be very short, right? It can do that maybe some things in parallel, but there is the phase where your application starts running, right? And your application very often has some code that needs to be executed in the beginning of your application runtime, but it is the same still one runtime. This is a single process. Now, if we look at the native image, how it runs that. So you first need to build the native image. So you take your application and you feed that to the native image utility, which is a part of the GraalVM distribution. And we call that process the build time. During the build time, your application is initialized, compiled, and the executable is produced. And then there is the runtime of your application, where you run your application and then it starts doing things that it's supposed to be doing. This is two different processes, and they can be separated both geographically. You can build on one machine and run in another machine, and in time. So there are two completely separate runs of your application. What's a little bit even more confusing, during build time, some application logic from your application can be run. So the build time is a normal Java process that processes your application. It finds the classes, it looks which classes need to be loaded, and so forth. and it can initialize those classes, so it can run some code from those classes. This is very important. So this top part is the normal Java process, and the bottom part is the binary runtime. They're separate. If you kind of internalize the understanding of that there are two separate processes, you will be much more effective at using native image. Why is that? Because during the build, there are certain very important things that need to happen for the build to succeed, for your application to run then later. So what's the input for that is your application. It's your application classes, libraries, the JDK starting library classes, the runtime classes that will be used to provide, for example, the garbage collection implementation for running your application there. And all that is available in the form of bytecode. The thing here is that you need all the bytecode be available there. It gets analyzed, it gets initialized. The heap of your application of the pre-initialized object is snapshotted. All that together with the compiled code is written out to the binary. And then that binary can run very, very fast. Let me just show that for you very, very quickly. So what I have here, is actually a very simple Java primes, Java primes web Micronaut application that computes the prime numbers, right? So Micronaut is an application framework that is very, very good, nice and modern. So here we have a controller and it does just computing prime numbers. It's very simple, very fast. And I can do GraalVM run it just to show you that this is the normal application. It will generate the run, it will start, and then it will run this. And if we open that in the browser, so what localhost 8080 primes, it will return us some prime numbers. Doesn't exactly, the logic is synthetic here, so you don't need to consider yourself very much. So what we can do now, we can also run the Gradle, something called native image build. And Micronaut uses the build plugin that GraalVM team provides. Maybe I need clean. I hope this works. It will run here for a few minutes. So let's talk while we're doing this. I want you to show how I build the native image, and I want to talk about the certain things that happen during the build, so you understand better what is happening, right? So we run the native image task, and this uses the GraalVM distribution that I currently have as my JDK here installed, and it starts initializing my application and compiling that. So first it compiles the class list, all the classes that will ever be run in our application. There will be no dynamic class loading of third-party plugins or random classes that you download from the internet during the runtime of our application. There is literally nothing that deals with the bytecode interpretation or compilation in the final executable. It's all stripped out. Those classes are set up and then they initialize, and then the native image utility, what it does, it statically analyzes your application and it builds the class universe, and it figures out which classes can be reached and which classes cannot be reached in your application. This is a reasonably time-consuming and memory-consuming process. It usually takes on this M1 Mac running non-M Mac M1 Java-based GraalVM. It takes a few minutes, like 2, maybe 3 with Zoom, we'll see. But what's happening is that the application is being compiled and initialized and compiled. So what I'm trying to say here is that it's very, very important that all the classes are, which is all the classes will be in our application. They need to be available on the build time. That poses a challenge with certain dynamic features of Java that your application might be using. So namely, those are the reflection, creation of generating dynamic proxies, loading the resources, because those are files, and they are not, the static analysis cannot figure out which files you want to use. If you want to serve your users a JavaScript file or an image, you don't do that using the class, right? You use it, you send it bytes, or you say like, oh, get me class loader, get resource, and you load the bytes and serve that. So the static analysis cannot see through that, because the names of those could be dynamic. Those are dynamic features. So during the build time, it cannot actually include those classes by itself. So what it needs you as a developer to provide the hints and configuration what you want to include. This is where very many people get scared, but actually it's not that bad. Literally not that bad. The configuration file is just a JSON file that you can write by hand. The configuration file is also something that your application framework can provide for you, because if it knows that it needs to initialize certain things the way it needs, it can provide configuration. Libraries can provide configuration built into them. So if you have a library and you want your library to be compatible and work well with the native image build, you can ask the maintainers to maybe look into providing config. And you can also generate this config automatically using a tracing Java agent. What it means, it means that you can run your application using Java, normal Java with a JIT, with a Java agent attached. And then you execute the code path, and it will record all the usages of all things that needs to be configured, and it will output the configuration file for you. This is very neat. One thing that you might want to use for that is running your tests, because during the tests, you normally execute the code path for your application, right? So it will generate the configuration for you. And it's a simple JSON files that you put into a jar, or you feed it to the native image utility through the parameter command line option, and then it will work splendidly. You can put it into the meta-int directory. You can even make the Java agent that is available as a part of the GraalVM distribution out of the box for you. You can make it generate the configuration for you into the correct locations, and then it will be picked up from there automatically. Right? Wait, how do I go to? I want to go here. Right, so our application built here, because it uses Micronaut, and Micronaut takes care of configuring your application for native image. And Micronaut also uses the ahead of time annotation, like annotation processing to configure the dependency injection graphs and to configure reflection usages and everything. So it works very nicely with GraalVM native image mode. So it's all nice and good. We compiled now this application here. Wait, this application. So if we do ls-la this application, what you can see in human terms, you can see that this is a 50 megabyte archive we can run, and this is our application. It starts up really fast. On this M1, it starts for some reason for 1/3 of a second. I don't know what's up with that. Normally, if I run any other example here, for example, on my cloud machine, on my cloud machine, it's a different demo. So if I do build native image application, it starts in 50 milliseconds, right? So this is the numbers that you normally would see. I don't know what's up with the M1 Mac, that it's slower than that. It's literally the same application, and on my M Mac, it takes 300 milliseconds. I haven't had a chance to debug that yet. Right, so this is our application. It runs on our machine, right? It runs on our machine. I can also access it here. You can see that it still provides me the prime numbers. And this is a cool thing here. If I do the activity monitor and I do the application, right? Our application takes, where's the memory? Memory. Our application takes 50 megabytes, 60 megabytes of RAM. This is the whole This is the whole RSS of our application. So we can have a small microservice that runs in under 100 megabytes of RAM during actually usage, right? So it's not the idle, just let's start our application. It's actually the application serves requests, creates buffers, uses netty underneath, and so on. So this is very, very convenient for our microservices here. So that's why you want to overcome the configuration for your build, and you want to figure it out. So configuration is not even the biggest misunderstood feature of native image. One of the biggest things are the class initialization. Because we have two different times where our application can be run, we also have, what do we have? We have 2 times where the class can be initialized. And by default, classes should be initialized at runtime. You can configure them to be initialized at build time specifically if you want. This is an advanced feature because at build time, you cannot run all code. For example, if your code creates running threads or opens file sockets, then those cannot be reasonably transferred from the build time to runtime. So the build will fail at you and yell that certain things are not supported. And you need to understand that's because the class was tried to initialize at build time, and you should be doing that. That is for the compiler to decide that certain classes are safe and initialize them if needed, or for the framework authors to carefully tweak what they initialize and then give the result to you. So, but there can be some errors that you can see with regard to class initialization. And then after that, this is the executable, right? So this is, if I do, what do I do? File, this is my application. This is currently on a Mac. This is the Mac executable, I think for AMD, right? And if I do, what else can I do? I think it's O2, right? Is it O2? Yeah, so it shows what it's linked against, right? So those are the dynamic libraries that we're normally linking against. There is no JVM, so it just directly links to libc, and you can move this around, and this is a standalone file. Of course, if you want to deploy to the cloud, what you want to have a Linux executable. So there's currently no cross compilation, so you need to build it either for the cloud that you on the cloud where you're trying to run it, or you build it in a Docker container, or you just get a Linux machine. But there are some references and scenarios that explain how to build. I have a project for different operating systems. For example, you can use GitHub Actions to build your project for Windows, Linux, Mac OS. There are a number of projects that do that. There was a question from Brian, a quick mention about static compilation and glibc and the differences. So normally, when you build it without anything, it will link dynamically libc implementation. That this is what you would expect. What you also can do, you can build a statically linked native image, which will use a muscle C implementation. There are instructions on the website. It's a little bit like you need to prepare the environment where you build, but the build will run normally the same. And then it will be a fully statically linked executable that will statically include the libc implementation as well. So what that means is, that you can take that application and put it into any environment without any, so the environment doesn't have to provide those dynamic libraries as well. So here, right, if I want to run this application, I need to have those things in place. I need to have them available for my application because it will call into them. So statically linked native image will not depend on any third-party dynamic libraries, which means that you can take that, you can put it literally in the from scratch Docker container, which is the empty Docker container, and it will run there. And you can do various things there. So you can explore things, but here is the slide where I want to talk about that. So when you want to put your application in Docker container, you want to use Slim based images because the application is fully self-contained. It doesn't need a lot from your environment. So if you can use the Slim Linux, you should. You don't have to have the JVM in that. You can even use the distroless based images, which is sort of a even more reduced Docker image effort by Google Container Tools project. You need to build your native image specifically for that. And then if you build with static and link against muscle C, the muscle libc, then you can use a from scratch Docker image, and it will literally be one Docker image with empty, with just your application, which is very, very cool. Right. Oh no, I didn't want to click that. Right. So, and then you need to run it. And at runtime, there are certain different configuration options that you need to understand to run. First, you can configure memory usage for the native image. Native image runs with the JVM, with the garbage collector enabled. So you can configure how much memory it takes and how much memory you want to allocate to the heap. You can print the stats about GC. You can also even include the default values for the heap sizes and build time if you want to do that, which is very handy if you, for example, build not the cloud service, but if you build like a command line utility that you want to send to people, then you can say like, I want my application to take like 50 megabytes of RAM. And if you need more, then do the garbage collection within that 50 megabytes, but don't like consume 2 gigabytes to do something, right? And then people will be like, oh, very good. This utility uses just a little bit of RAM. How interesting. And you're like, yeah, I coded that in Java or maybe Kotlin. So yeah, Kotlin, right? Now the languages, they of course support it. So the native image utility works on the bytecode level. So it doesn't matter what you use to produce the bytecode, that as long as the bytecode is valid and normal, it will chew through that and then produce your native binary. So you can configure the memory. You can use some enterprise features to enable even better peak throughput and latency of the native images. And I think this is reasonably interesting. Those are enterprise features, so you might want to consider whether you want it or not. But you can significantly increase the performance of the native binary that you're using that. So for example, if I in a recent experiment, I had the application and I ran it twice. One is just compiling normally, and the other one compiling with all the performance enhancement that Enterprise Edition can provide to that at that time. Right, and I almost doubled the peak throughput for, not peak throughput, the average throughput of my application then. The numbers in vacuum don't say anything, but the comparison is like with PGO and everything, it was like what, almost twice faster, like 60% and 70% faster, which is very interesting. So if you have that requirement, you might want to consider that. If you don't have that requirement on the peak throughput, then yeah, you probably want to start with the community edition for simplicity. So if you think about, and as Brian mentions, the throughput comparison to the plain old JVM, this is a little bit vague question, because first, it depends very heavily on the workload. Second, it very much depends on the JVM. If you take, for example, like OpenJDK distribution versus GraalVM Enterprise Edition, the JIT compiler will kick in and change your numbers very, very much. But the thing is, if you have short-lived processes, then the native image will be much, much better, right? Because the JIT takes time to warm up and everything. If you have resource-constrained environment, then JIT might not, the JIT will take even more time to actually process everything and run and everything. So on long term, your native image will probably be slower. I would like in the ballpark, I would expect the community edition be something like 40% slower than your worn up normal OpenJDK distribution. But it might use less memory, so you might be able to like just scale it differently. But it will be slower. If you just run it for all normal experiments that you probably will run, it will be slower. And then your Enterprise Edition with PGO and everything will be very much similar to your JVM with the JIT. maybe like a little bit slower or something like this. And the team is working on that. And I'm not sure how much progress or how soon the progress can come, but this is definitely something that the team is exploring. Right, so I've talked about Micronaut a little bit. It's an excellent framework. I want to show one example there because I want to show how test containers work. But I won't do that the full blown. I will just say that if you want, Micronaut has excellent support for test containers and writing integration tests. So you can encode your third-party service dependencies as your Java objects, and you can store them and you can use them during your test phase. And so when you run your tests, so here for this application, for example, what it will do, it will spin up the Kafka container and programmatically manage its lifecycle, and it will be very, very good. And your application test will run against that actual Kafka instance. And there are other databases and search engines and Hadoops and everything else, right? So just a little plug. Sadly, we didn't get to that, but we'll go further with the last few slides that we have here, right? Micronaut is great. Spring is also great. Spring is working on the Spring native support, which is a separate project. You need to enable that in the Spring initializer. It will enable certain way how Spring configures itself for your application runtime. But all in all, it gives you a very nice, the same native look and feel and performance, and the team is not stopping. So you can try that now, but you can also expect much more benefits come in the future. So around now, the Spring team and the GraalVM team together got to the point where the compatibility is at a good level, and now it's time for the optimizations. So you can see that a recent native 0.10 release got much better at the startup time, which means the application doesn't do that much during the startup time of the runtime, right? It does much more at the build time, or just doesn't do unnecessary things. The container sizes are going lower. So it's all a good work at optimizing Spring and GraalVM native image combination is ongoing. You can watch the presentation by Sebastian Deluza. It's an excellent engineer. They lead for the Spring native project. I think it's if you are interested, you should follow the Spring native, even if just for better understanding how a very large, mature, and complex application framework that depends on very many things being done dynamically can work with GraalVM native image, right? Because Spring uses reflection, Spring uses the dynamic proxies, Spring uses resources, Spring uses this and that, everything, right? Spring uses literally everything. So, and if Spring works, I'm pretty sure we can figure out how small libraries work with on the native image. So the work is not stopping and the progress is going forward. And this is something that I'm personally very, very excited in looking forward. Right. And it's not only actually the web applications in the cloud. The applicability of native image is much wider than that. There are other tools. There is the Maven, Daemon, and SBT native client, where your build tools have the client, the server part, and the client is native image. So it starts really fast, and the Daemon does the hard work, which is very cool. There is the support for native image that gets into popular libraries. For example, the AWS SDK for Java recently got support for native image. So you can use that out of the box with native image, which is very cool. Lightbend rewrote, there are some Kubernetes operators from Go to Scala. And with native image, they get the similar performance, but still it's Scala. This is something that they know how to do very well. It's much easier for them, and so on. And then there are even more innovation happening on the GraalVM team. So with the recent Java on Truffle announcement, you can even do some ahead of time compilation of a chunk of your application. It's a little bit awkward currently. It's not very convenient to do that, but you can sort of have a part of your application pre-compiled and part of your application go through this Truffle interpreter and do stuff dynamically, which is also very interesting. Right. So all in all, there are a bunch of resources that you need to kind of sort of look at when you do work with native image, but your application frameworks that you're using currently probably support that or work on supporting that. For the command line applications, Pika CLI is a great framework, and Brian in the chat referenced a template that he created, right? So it's all, the world is your oyster, right? There are more and more people using this, and there are more and more people looking into how to use that in their cloud environments and make it much better. Right, so all that, we have literally 2-3 minutes for the questions. I think this is mostly everything that I wanted to show you. If there are no questions, we can talk about something, or we can, if there are questions, I'd be happy to answer. Oh, I know, while you're thinking about the question, I will run that application test that I wanted to show you. Check this out. So this is my Micronaut application there, right? And I will do Maven verify, and it will run the test. It's a very simple application, sample application from a tutorial how to write Micronaut in Kafka. And then I just want to show you how the tests run. You can see there that it integrates with test containers. They talk to the Docker that I have here, and then it runs the tests, starting and cleaning up the containers automatically. So Brian asked, do you recommend not using native image for long-running applications? This is a complex question, right? If performance is peak performance and peak throughput, what you are looking for, then probably not, right? I would recommend running with a JIT. It's simpler and everything. If you want, you can use native images for long-running applications. You just pack it more neatly in memory, and then you scale horizontally as you scale, like, for example, Go or Node.js applications by process, not by thread. And then it's totally fine. It's perfectly fine. Something broke. It's not supposed to be broken here. Let's not look at that. Let's look back at here. I don't know, something broke with my Docker. Right. Dmitry is asking, framework support is mature, but are there known APMs that work well with native images? This is very interesting. Normally, you would like to monitor native images the same way you monitor, say, Go applications. You build in support for metrics, and then you use adapters that send the data to your APM of the choice, right? You cannot use the JVM TI and Java agents with the native image, because it cannot attach to the binary, right? Because there's no class redefinitions or anything like that. It's all fixed in place. So you cannot use the normal approach to how you get monitoring and things. You can use other things. So like Micrometer as a framework, as the application library to collect the metrics and send them somewhere, works totally fine. There's an effort to enable the Java flight recording support in native images, so you can build your native image with the Java flight recording support, and then it can generate the events and files, and you can monitor your application that way. But there is no attaching and redefining the talk in the thing, right? And then the last question before they kick me out, how the GC works with native images. The GC implementation comes from the Substrate VM project, which is there's a Java implementation of by default, the generational scavenger, which is a sort of simple generational GC, old generation, young generation, the cycles. It's very straightforward and sort of optimized for not doing any work while the application is working. So there could be longer stop the world pauses when you run with large heaps, but if you run with small heaps, the error will be barely noticeable. And it works the same way as it works with other GC implementations, right? So your application imagines that the memory is infinite, and there is something that allocates the objects and then collects the memory and frees the memory and tells where to allocate other objects. And there is just different implementations of the GC algorithm available in the Enterprise Edition. So you can link in, for example, G1 GC. That's it. We don't have any more time. If there are any other questions, I hope you enjoyed this. find me on Twitter, ping me on Twitter. We'll see how it works. And then thank you very much for coming. Yeah, see ya.